title is Harish Chandra modules of quantizations of nilpotent orbits, and it's an attempt, let's put it this way, to algebraically understand unitary representations of reality groups, or at least, understand some algebraic objects, or I should say algebra geometric objects, supposedly related to unitary representations. And so here is a plan. I'll first talk about generalities about Harish Chandra modules. That's very classical Lie theory. Then I'll discuss something called restriction functors, which is a tool to study such modules. And then I will explain some results, and also, if time permits, I will explain ideas of the approach. So let me start with a general setting needed to talk about equivariant things. Curly A is, for time being, is going to be some associative algebra over the complex numbers. K is going to be an algebraic group. I don't require it to be connected in general. I wanted to act rationally on A, of course, by algebra automorphisms. And I want it to have a so-called quantum comoment map. So what it is a linear map from this funny symbol, which is the Lie algebra of K, to A. And I want it to be equivariant with respect to the group K. And I want it to satisfy the following condition. So on the left-hand side, I just have the bracket with the image of Xi. So Xi is an element of K. And on the right-hand side, I have the derivation of my algebra, which comes from the action of the group X rationally, so I can in particular differentiate the action. Okay. So here is a classical example of this. Would you mind muting ourselves if nobody expects to ask a question? Oh, I don't know. Thanks. So here's a classical example of this situation. I take a semi-simple algebraic group G, and then I take some algebraic group homomorphism from K to G. And my A is going to be the universal enveloping algebra. Phi is just the induced homomorphism between the Lie algebras of K and G. Okay, this certainly satisfies all properties are required in the previous slide. Now, let me give a definition of a twisted equivariant module in this situation. I pick a K-invariant linear function on the Lie algebra. Let me call it kappa. And then I want to define a K kappa equivariant A module. So this is an A module M, which is equipped with a rational representation of the group K. So again, I can differentiate this representation, getting an action of a Lie algebra. And I want two conditions. I want the module structure to be equivariant. This is usually referred to as weakly equivariant module. And I want the following strong equivalence condition. So if I apply the derivation induced by Xi to a vector M, it's phi Xi times M minus the pairing of chi and Xi. Okay. So if you started the modules at some point, this should look like a familiar definition. Now, when kappa is equal to 0, then it's a usual definition of a strongly equivariant module. Then the situation where I'm mostly going to apply this definition is the situation of the previous example. So I want to consider an algebraic group homomorphism as before, and I wanted to give an isomorphism between the Lie algebra of K and a symmetrical subalgebra of G. So the fixed point of some Lie algebra involution. I would like to point out that K doesn't need to be a subgroup of G for the purposes of this definition. So this homomorphism here can have finite harmony. And then a very classical object in Lie representation theory is a Harish Chandra UGK module. This is just a finitely generated K equivalent, so no character here, module over UG. Okay. So why do we care about these guys? In the situation when K is a subgroup of G, then these modules are related to representations of the real form of G. In particular, if you start with a unitary representation, there is a procedure to get Harish Chandra UGK module out. Now, if K is not a subgroup, if there is a kernel, then the corresponding module is going to be related to representations of some non-linear cover of our group. And it's also an interesting situation that we want to consider. So then, question is, can we give some reasonable classification of Harish Chandra modules? The answer is yes, you can do so for U of G if you use the Bernstein theorem. But I want to ask a more specific question. Suppose that I have a primitive ideal in the universal enveloping algebra. And primitive ideal is just the annihilate of some irreducible representation. So what I want to do is to classify all irreducible Harish Chandra modules M with a given annihilate. Okay, so I want to classify irreducible Harish Chandra modules according to the annihilate. That is something that the localization theorem won't be able to tell you. Okay. Of course, everything is going to depend on which kind of ideal I'm going to pick. And I want ideals which are associated to some nice geometry, because in the end of the day, the classification is going to be geometric. And here is what I'm going to care about. I'm going to care about the so-called unipotent primitive ideals that were defined in the full generality last year by myself, Lucas Mason-Brown, and Dmitry Matveyevsky. And each of these ideals is associated to equivariant covers of nilpotent G orbits. Okay, so that's going to be a very special kind of ideals. So let me tell you a little bit more about them. I want to concentrate, Sasha?
Just there was some alarm here, but now it's off. Yeah. So, okay, go on.
All right. So I want to impose an additional assumption. So I want to start with an important orbit O in G, and I want the codimension of the boundary to be at least 4. Okay, that's a fairly restrictive assumption. However, if we care about the so-called rigid orbits, rigid means that this cannot be induced by Listig-Spaltenstein induction from an orbiting a proper levy. You can also call them cuspidal if you wish. Then all rigid orbits but 6 in the exceptional Lie algebras satisfy this condition. Okay, and in fact, the 6 should be possible to handle them by techniques pretty similar to what I'm going to explain, but it's more technically complicated and currently is not done. So somehow, let me place this restriction to some context. A typical procedure how you would study representations of a group would be induction. In particular, you would like maybe to study representations of real groups, including unitary representations by induction. And representations which correspond to rigid orbits are ones that you cannot induce from anything. Sort of cuspidal cases, and you want to understand them first. Of course, whether everything is induced from a rigid orbit is a big open question. But that's sort of these guys are certainly those which cannot be induced. Now, we have a certain procedure, and I will, it may become clear from the next slide of how this works. From this orbit O, I can produce an ideal, which I will call I sub O. And it has the following two properties. So first of all, this ideal is maximal, and every maximal ideal is primitive. Okay. Second of all, if I form the quotient, let me call it now A, the quotient of the universal enveloping algebra by the ideal I. Well, first of all, it comes with the Poisson-Karebe-Goffin filtration, but this filtration is a bit defective. You can modify it, so there is some a priori different filtration, such that the associated gradient of A with respect to this filtration is the algebra of regular functions on the nilpotent orbit O. And that's an isomorphism of graded Poisson algebras. So this fellow A can be called the quantization of this algebra of functions.
Right. These conditions have so far nothing to do with this codimension 4 condition, right?
These conditions don't have anything to do with codimension 4. That's right. So if you have any orbit O, and you can also consider certain covers of this orbit, then these conditions are going to be satisfied. So I will comment about this condition maybe a bit later. But it's got sort of simplified notation a little bit. For example, you don't need to care about covers. In general, if your codimension is codimension of the boundary is 2, different covers will give rise to the same idea. 2 different covers will give rise to different ideas. Here, all covers give rise to the same idea. Okay. So a little remark. So this was this condition number 2. Let's keep it in our hearts for a moment. The fielded algebras, which satisfy this condition 2, meaning quantizations of this algebra of regular functions, are classified by the second complex cohomology of the orbit. Okay, that's a vector space. Wouldn't be true if the codimension condition wasn't satisfied. And then what we pick is the quantization corresponding to parameter 0. That's the so-called canonical quantization. If our orbit is rigid, or more generally so-called birationally rigid, then the second cohomology is just 0. So in fact, there is a unique quantization. You can just think that I'm dealing with a unique quantization of the algebra of functions on the nilpotent orbit. Okay.
I'm sorry, I'm confused. I'm just probably missing something. Suppose O is the regular nilpotent orbit.
Yes.
Then second cohomology is 0, right?
Cartan.
So it's
sorry. Yes. Second. Yes, that's right, Sash. But the parameter space is sorry. Yes, the parameter space is higher. Is bigger in this case.
Yes. So then I don't understand. So
in this case, so I impose this codimension
condition.
That's right. Under the codimension 4 condition, this is the parameter space, and if the codimension is 2, then the parameter space is large. Okay. All right. So in fact, what we are doing, our paper works for all quantizations, not just canonical ones. But somehow, for what we are doing, this codimension 4 condition is absolutely crucial. If one omits that, then we don't know how to classify things. Maybe a bit later I will elaborate on why. Okay, are there any questions at this point?
Maybe I have some naive question. Could you give a less exotic example when this codimension condition is satisfied, right? I mean, for instance, for SLN, for which orbits?
For SLN, it means that in the partition, all entries are pairwise different.
Sorry?
It means that, orbits in a Slang are parameterized by partitions.
Yeah.
And it means that the parts are pairwise distinct.
Okay.
For example, the minimal orbit certainly satisfies this condition, but certainly does not satisfy your partition condition.
Wait. Yes, Misha, you're right. You need to transpose. So the columns are all distinct. Sorry.
Thanks.
All right. Let me give you some examples. So let me pick G to be SL3. And let me pick K to be SL2, which subjects onto SL3 inside of SL3. And let me pick the minimal nilpotent orbit. The Jordan type is going to be 2, 1. Okay. And the dimension is going to be 4. Then, the closure admits a resolution, which is T star of P2. And all quantizations are global twisted differential operators on P2. I want to pick the canonical one, and that's global differential operators with coefficients in 1/2 of the canonical class. The canonical class is O minus 3. So I twist by -3 over 2. Okay. Then we can apply the localization theorem and get classification of all Harish Chandra modules for this quantization. So this parameter is regular, therefore the localization theorem just holds. Okay. What do we get? Well, these D modules are parameterized by twisted equivalent local systems of orbits. And we have 2 orbits. There is the open orbit. It looks like this. It's SO3 modulus the normalize of the torus. Well, there is no twist because this group doesn't have any homomorphisms to 3 times. So I'm just looking at local systems on this orbit, and there are 2 of them. Because the component group here is Z mod 2Z. So what I'm going to get is 2 honestly SL3 equivalent Harish Chandra modules. These guys are going to correspond to representations of SL3R if you are into representations of real groups. Now, there is also the closed orbit, which is P1. And it's going to support 1 twisted local system, which is because of our twist, the system is only going to be SL2 equivalent. So the action won't factor through SL3. Okay. So I have 3 Harish Chandra modules in this case. The next example that I want to consider is SP4. And I take the symmetric subalgebra GL2 inside of SP4. O is going to be the minimal orbit. Okay, and the Jordan type is going to be 2, 1, 1. Okay. Dimension is still 4. This orbit is easy to describe. The closure is just the quotient of C4 by the action of plus minus 1. And I have only 1 quantization. That's what I do. I take the Weyl algebra of C4. And I take invariance with respect to plus minus 1. Okay. Now, if I want Harish Chandra modules, I will need to pick a 2-fold cover of GL2. And these are so-called metaplectic representations. Turns out that there are 4 of them. And what you do is the following. So inside of C4, you have 2 Lagrangian subspaces, which are GL2 equivalent. If your C4 is T star of C2, then you take, C2 and the cotangent factor. And we can quantize them. And on the quantization, we still have the quantize them to modules of, this WC4, which are differential operators on C2. And on this quantization, I still have an action of plus minus 1, so I can take isotypic components. And so total I get 4 irreducible modules. And they're only going to be equivalent with respect to twofold cover of GL2. Why? They're weakly equivalent with respect to GL2, all right. But if you want strong equivalence, you will need to take 1/2 of is determinant to -1 as a character. All right. So these are examples that actually play a very crucial role in the general theory. So we should keep them in mind. All right. So to summarize this discussion, what do I want to do? So I start with an nilpotent orbit with this codimension for condition. I take its canonical quantization. And then I want to classify Harish Chandra modules over this quantization. Why? For example, there is supposed to be the notion of a unipotent representation of a real semi-simple group. And outside of the complex case, I would say there is no good definition of what this means. But representations which correspond to this Harish Chandra module that I'm about to classify are all supposed to be unipotent. Okay, so that's a part of motivation of why I want to study this problem. All right, so now let me explain a key ingredient to study this.
Can I ask a question? So what is the importance of considering this canonical quantization? In what sense it is canonical? I mean, canonical just means that it corresponds to 0 and this H2, right? I mean, when is it? But what does canonical mean for you in some sense?
You don't ask at least what quantization means for me.
Generally, please.
So there is this conjectural thing called the orbit method. It sort of tells you that representations of reductive groups should correspond to some kind of nilpotent orbit. So maybe there are covers, or maybe some, some twisted local systems in their covers, something like that. And among all, nilpotent should be coadjoint. Okay, coadjoint orbits are their covers of some local systems and such. Among all coadjoint orbits and their covers, our favorite ones are nilpotent. Sasha, would you agree with this sentiment? I just want to put you on record.
I mean, my question was that somehow you can play this game by considering, I mean, other quantizations of.
Yes, Sasha, but I'm answering your question. I just want to make sure that you're satisfied with my answer so far. So we all like nilpotent orbits, right?
Yes.
And then there is a natural correspondence between equivalent covers of coadjoint orbits and quantizations of covers of nilpotent orbits. You can write a natural bijection between the two. And under this bijection, the nilpotent orbits and their covers will correspond to canonical quantizations of covers. So that's why I care about canonical quantizations. As I said, what I'm going to explain is going to work for all quantizations. Canonicals are somewhat, somewhat more canonical than others, and somewhat easier. So does this answer your question?
I mean, what I was hoping for is a kind of explicit definition of what canonical means, but somehow.
Well, I mean, this parameterization is also natural. And certainly if you have a parameterization of quantizations by points of a vector space, and of course, if you have a vector space, then you have a single distinguished point in it, which is 0.
Fine. Let's continue.
Okay. So I impose this restriction on the codimension. The codimension is big O equals in form. And so if I take a K orbit, let me call it OK, inside of O intersected with orthogonal of K, this orbit is always Lagrangian inside of the G orbit. It's a nice exercise. It's actually the fixed point locus of anti-symplectic involution. And therefore, the codimensions are just divided by 2, the dimensions and codimensions. And therefore, the codimension of the complement to the closure of this orbit, OK, is big or equal than 2. It is actually the condition that we need to keep going, as it turns out. Now, under this condition, something good happens. Namely, if you take an irreducible Harish Chandra module over this quantization A, then its associated variety, and associated variety is the following. So you take some good filtration on your M, then you take the associated graded with respect to this good filtration. It's actually a modulo of functions on the space, and then you take the support. So that's the associated variety. So under this codimension condition, the associated variety is guaranteed to be irreducible. So it's just a closure of one of these guys. It's just one of these guys. Okay. In general, if you don't impose this condition, then associated variety may fail to be reducible. You already see it in the case of SL2, for example. So in any case, we fix this K orbit OK, and let's pick some point. Let's call it chi. Starting from this point, we can get the stabilizer, which I call K sub chi. This group is not reductive, so let's take its reductive part. And I would like to emphasize that this doesn't need to be connected, maybe a disconnected group. And I want to consider the canonical bundle of OK. This is a equivariant vector bundle. Restricting to a point, I get a character of my group R. And I want to multiply this character by 1/2. Okay, I will call this kappa. So now it's a character of this group of the algebra R. Okay. And I want to consider the following 2 categories. The first is a category of R kappa mod, and it's a very easy category. It's a finite dimensional modules over this algebraic group, where the algebra acts by scalar kappa. In particular, if my group were connected, this category is just equivalent to the category of vector spaces. As it is, it's a category of projective representations of the component group of this with a specified Schur multiplier. And it's a semi-simple category. It's like an elementary representation theoretic object. On the other hand, I want to understand the category of all Harish Chandra AK modules, which are supported on the closure of the orbit OK. Okay, and I call it like so. So the entire category splits the direct sum as well. I mean, at least the set of simples splits as a direct union, as the joint union of simples in this category. Okay, and actually the category splits into the direct sum. Now, the 2 categories are actually related, and that's the purpose of this restriction function, which goes into the title of this section. Namely, a more general construction, if I start with an arbitrary Harish Chandra module over U of G, then I can restrict it to the slot of a slice and get a R equivariant Harish Chandra module over the W algebra. So this called W is a W algebra, which quantizes the functions on the slot of a slice too. And from some perspective, this functor literally takes the restriction to the slice in the non-commutative set. But I'm not dealing with all. So this category takes some effort to define. I will actually don't need to know what the definition is, because in our situation, things simplify. Namely, by a morally similar restriction procedure, I can take my ideal I that I mod out. I can restrict it to the slice, and I get a codimension 1 ideal in the W. Okay. and it must act by 0 on the restriction of M. And so, you know, you have an associative algebra. Inside, you have a codimension 1 ideal, which acts trivially on the representation. It means that this representation carries no information. Okay? The only information about the target is the action of this group R. And it turns out that since this quantization is canonical, I'm going to leave to land in the category of R kappa models, which is a semi-simple category. Okay. So I can start with my Harish Chandra module supported on the closure of OK, and I get a projective representation of the component group of R. Okay, so let me tell you a bit more about this factor. So first, let me explain some properties that it has. So it turns out that it's a fully faithful embedding. In particular, this category of Harish Chandra modules is semi-simple. Okay. And second, if my situation with codimension improves even further, and codimension of the boundary of the k-orbit is at least 3, then this functor is an equivalence. And I've already finished my classification problem. So I'm already able to classify the irreducibles in my category of Harish Chandra modules. How? Well, I need to understand this. I need to compute this character. This character gives me a Schur multiplier for the component group, and I just look at all irreducible projective representations with the Schur multiplier. So the problem solved. In general, this functor may fail to be an equivalence. It's just a fully faithful embedding. And so what I need to understand which irreducible object here lie in the image. And then my classification problem is solved. So that's one thing. And second thing is, well, I told you that the functor is there. I never told you how to determine what it does to a Harish Chandra module. So let me tell you that. So let me start with a Harish Chandra module M, and then I can pick a good filtration. I can pass to an associated graded. Associated graded leaves on the closure of O. Okay, let me restrict it to the open part. We consider this. And then, following a result of Vogel from some time ago, what I get is a twisted local system with half canonical twist. Okay? On this orbit, okay. And to give such a local system is to give this R kappa module just by restriction to a point.
Can I ask a stupid question? So why is it, I mean, when you restrict it, it's a coherent sheaf, right?
Yes.
So why, in what sense is it a local system?
This coherent sheaf, well, its restriction to OK will be forced to be scheme theoretically supported instead of set theoretically supported.
Okay, fine. So, but
then,
in what sense is it a local? Oh, you mean when you say local system? What do you mean? I mean, do you mean that just a covariant coherent sheaf, or?
No, just a twisted local system. What is an equivariant coherent sheaf on an orbit? It's a representation of the stabilizer. Right?
Yes.
This representation may so happen to restrict to a character on the Lie algebra. In this case, it's a twisted local system. You can define the action of vector fields by passing to a quasi-classical limit as well. For example, if you deal with a Harish Chandra bimodule, then when you do this, you get a Poisson module. And Poisson module on a smooth symplectic variety is nothing else but a D module.
Okay, fine.
So for Harish Chandra modules, you have something similar. So just, Sasha, it's a general principle that if you pass to a quasi-classical limit, you still remember some part of this non-commutative structure, which in this case is just a twisted local system.
And what's the difference between twisted local system and just local system?
Because I don't twist with a line bundle, I twist with half of a line bundle. So a twisted local system
module which is all coherent. Yeah, that's what you say.
Yes.
It's a twisted demodule which is all coherent.
Yes.
Okay, thanks.
And the twist may not be integral. It's actually very important. Okay, are there any further questions? Okay, let me tell you two examples of how, how this, so I told you that I have a fully faithful embedding from Harish Chandra modules to twisted local systems. And in my two examples from above, I have already classified all irreducible Harish Chandra modules. And I need to tell you how they relate to twisted local systems. So let's start with an SL3 example where I have a minimal orbit. The group K is SL2, and you can compute this intersection. It's going to be the intersection with, well, symmetric matrices. You can ask which symmetric matrices lie in the minimal nilpotent orbit. You can get an answer. It's a single SL3 orbit. And it looks like this. You take C2, you remove the origin, and you mod out by the cyclic group of order 4, by symplectic transformations. And so there is no twist. That's a symplectic variety. The canonical bundle is trivial. And my category of R kappa modules is just the modules over this group. Modules over cyclic group of order 4. Now, not surprisingly, when I do this to SO equivalent, when I do my restriction function to SO equivalent irreducible Harish Chandra modules, of which I have 2, I have SO3 equivalent local systems. Okay, and SO3 equivalent local system correspond to representations of Z mod for Z with a generator X by 1. Okay, with action factors through Z mod 2Z. And both this, so by counting, Harish Chandra modules versus local systems, both of them must lie in the image. But then I have one Harish Chandra module which is not SL3 equivalent, which is only SL2 equivalent. And it goes to one of the remaining 2 local systems. Okay, you can actually figure out which one. Let me leave it as an exercise. And therefore, well, I have a category with 3 objects, and it's full embedding to a category with 4 objects. This embedding cannot be an equivalence. So I have one simple in the target category missing, which creates a lot of trouble for this theory. On the other hand, when I have the minimal nilpotent orbit in SP4, then this intersection of 4 with K perpendicular is 2 orbits. So what is O? It's C4 remove origin mod out by plus minus 1. And this orbits are this K orbits are just 2 GL2 equivalent C2 or modulo plus minus 1. Okay, so it leaves like this. For each of them, for each of the 2 orbits, my category of twisted equivalent representations is Z mod 2Z. And in this case, the restriction factor is an equivalence. Okay. So SL3 case, not an equivalence. SP4 case, equivalence. And finally, in the remaining, I don't know, 20 minutes or so, let me tell you about the main result, well, which is on this page. And then I'm going to tell you something about how this main result is proved. And if anybody has questions, I will be happy to answer. So, all right. So I want to again reemphasize that I'm under this codimension for condition, and we'll see a little bit later why I want to impose it finally. Then there is one theorem which is neat and cute, and one theorem which is still cute but less neat. Okay. So a cute theorem is that my functor, the restriction functor, which goes from this reducible Harish Chandra module supported on the closure of a given orbit to twisted equivalent modules over R. So again, let me reemphasize that this is something that you can compute with some effort, or more precisely, something that you can extract from the existing tables, more or less. So this functor is an equivalence under the following two conditions. One of the following conditions. Either K is inside of G, or your Lie algebra is of types BCD. So let's get back to the previous example. So in this case, you see, in example 1, everything was fine as long as I was dealing with SO3 equivalent models. For SO3 equivalent objects, I get an equivalence. So the only problem was with SL2 equivalent objects, but SL2 doesn't sit inside of SL3. Okay, only SL3 does. So there is no contradiction, at least of this theorem, in this example. So what does it tell us? So the case when K is inside of G is a case of representations of a real algebraic group. So this kind of modules for real algebraic groups are easy to classify. When you want nonlinear covers, then weird things can occur. And in the case when you are dealing with modules of SLM, essentially the only problematic case is when K is spin n, which again maps to SLM with kernel of order 2. You can show that you can actually compute this group R in all cases. You can show that there are no invariant linear functions on the Lie algebra. In particular, your category of twisted equivalent modules is just the category of usual equivalent modules, meaning modules of the component. And one can completely describe, well, sort of completely describe what lies in the image. Namely, it's a somewhat technical theorem, but the point is this: we have a bunch of elements in this component group. We can describe them explicitly up to some automorphism of this group. And then, so that's a typo, this would be R. And then a representation of the component group lies in the image of the restriction functor if and only if minus square root of -1 is not an eigenvalue of one of this chosen element of your representation. Okay, that's the answer. And that's how the answer in the SL3 case look like. Okay, so we pick, of genuine representations of this cyclic group of order 4, we pick just one. And you can say that with a choice of a generator, you pick one where this generator doesn't act by minus square root of -1. Questions?
So what is the number K here?
Some number, which you can compute. And I won't tell you what it is. So that's a little bit complicated. This depends on your partition. You either need to choose, you have this group is what? This group is a product, or the group in SLN is a product of the group R. is the product of a bunch of copies of O. And then depending on the parity, you either pick one of the generators of the component groups or you don't. Something like this. Does it sound like a satisfactory answer?
Yes.
All right. So let me explain how, or roughly speaking, this is proved. So what do we want to do? We kind of want to quantize certain singular Lagrangian subvarieties. Generally, you know, when you talk about quantizations of smooth Lagrangian subvarieties, this is not a problem. So there is a more or less a uniform answer. With singular Lagrangian subvarieties, it's more complicated. And somehow the issue essentially sits along of codimension 2 strata. So, you know, the codimension of the boundary for this K orbit is equal to 2. If it's equal to 3, then there is no problem. So what happens in that case, you take a quantization of the smooth part and you just push it forward. You take the global sections. And this gives you a Harish Chandra model. When the codimension of the boundary is 2, this fails to work. You can start with your quantization of the smooth part and discover that it doesn't have any global sections. That's what we see in that SL3 example. So what we really need to understand, we need to understand what happens along the codimension 2 strata, okay? And they come from codimension 4 orbits in the closure of the G orbit. So let's pick one of this orbit, let's call it O prime. Let's suppose that this intersection here is non-empty. And let's pick a K orbit inside of the intersection. It has now codimension 2 in the closure of OK. Now let's pick SL2 triple, E prime, H prime, and F prime. And we can do so that, you know, both nilpotent elements lie in the orthogonal of K. Then we can take the Losev slice in the G orbit. We got a 4-dimensional variety. And it's going to come with a symmetry which is centralized of the SL2 triple. That's a reductive group. It turns out that we can completely describe this thing and also its symmetry in all cases. And that's the ultimate reason why the codimension 4 condition is imposed. So it's one of the reasons. So first of all, you have known description along codimension 2 strata. Second of all, you have nice behavior coming from codimension of the boundary big O equals H. These are the two reasons. So let me tell you a little bit about this description. So in classical types, it's again classical result of Kraft and Prachese from the ages. And exceptional types, it's more recent. It's like 5 years ago by Fu, Juteau, Levy, and Sommers. So what does it look like? So in type A, this S prime, the slice to the G orbit of 4-dimensional variety is actually the closure of the minimal orbit in SL3. And the Q prime action just factors through PGL3. In types B, C, D, I have the minimal nilpotent orbit in SP4, and the action of Q prime factors through SO pi. Okay. And then in exceptional types, I have by this, or I have 3 exceptions. There are also exceptional dimension 4 singularities. For example, one of them, well, you take this guy, and then there is a preferred action of ±1 just by, you know, rescaling. And then you take the quotient. And that's one of the singularities which appears in type 7. Okay.
I'm confused. So can I just go back a second? So I can see the case when this codimension is equal to exactly 4, right?
Yes. So codimension 6 doesn't matter. Everything just pushes out of, essentially pushes out of locus. So somehow, what's going to happen is this. So I want to take my, okay, all right, let me explain what's going on. That's going to be on one of the next slides, but in any case. So what do you want to do? What do you want to do? You can convert, so you start with a local system on a smooth locus, twisted local system. You can quantize it. You have a genuine sheaf of modules over quantization of your G orbit, which leaves over the K orbit. Okay? And then what you want to do with this, you want to take the global sections and get your Harish Chandra modules that you are after. Harish Chandra modules that will give that local system. The problem, these global sections may be 0. And so in order to study this, I first want to push it to the codimension 2 strata. Okay? And it turns out that once I was able to do so, then everything else is not a problem. It then pushes further. Okay? So if you have, it's a crucial difference with usual coherent sheaves. If you have a coherent sheaf on an open subvariety, then it always extends to a coherent sheaf on an ambient variety. So exercise in Harsham. If you have modules over quantization, this is not the case. You can take the push forward, but the push forward doesn't need to be coherent or quasi-coherent. It's just some crazy sheaf. And what you're after getting coherent push forwards. So that's what you want to do. Okay. So there is this complete description of this dimension for singularities. And now let me start with this twisted equivalent module. Let's call it V. And I can convert it to twisted equivalent local system. Let's call it LV on the K element. So I need to observe the following two things. So there is an easier thing. And well, okay, so that's going to be a bit technical here. So first of all, if my representation V does come as a restriction of a Harish Chandra module, then the restriction of LV to the complement of 0 in the dimension for slice, that's going to be a quantization of a local system on a Lagrangian in that slice, actually coincides with the restriction with associated graded of certain Harish Chandra module restricted to this locus. So the associated graded will leave from S prime, then I can restrict it to the generic locus. And so what is this? So this restrict to S prime is some version of a restriction function. It goes from the category of Harish Chandra modules over the original quantization to the category of modules over slice quantization. Okay. The notation here is that this AS prime is a canonical quantization of the slice. In the two examples that I considered, we had that in the SL3 and SP4 example. So the algebra AS prime was described, and this group was described in these examples. So in fact, in these two examples, for these two singularities, this category here is just an honest category of Harish Chandra modules, like in the classical Lie theory. And I know how to describe the simple objects in this category. These are the two examples that I considered. And I know the images under, the restriction function. So if I, if I have my twisted local system, I can restrict it to the slice, and I can get an idea of what kind of Harish Chandra modules over A I can get. So the restrictions to this S prime should correspond to the twisted local systems, which arise in the examples I considered above. Well, if I have this one of these exceptional four-dimensional singularities, then this requires a separate definition. It's no longer classical Harish Chandra modules. And there are three exceptional cases we can classify these Harish Chandra modules in two of them. And the last one is too complicated. Then, okay, so that was an upper bound. So I can, this gives me an upper bound on which V I can expect to arise from Harish Chandra modules. I need a lower bound for each irreducible, say, twisted local system V. I need to have sufficient conditions for this local system to arise from Harish Chandra modules. And this is more difficult. So suppose that I indeed can do the following. So for each component of this intersection here, I can find a Harish Chandra module over the slice quantization, which will serve the restriction of the local system. Meaning that the associated gradient is global sections of this restriction. Then in fact, V lies in the image of the restriction factor. And that's a lower bound. And what's going to happen is this. So I have a unique quantization of this twisted local system. And I'm going to push it to the union of the open stratum and all codimension 2 stratum. What I'm going to get because of this condition, I'm going to get a quantization of the push forward of this local system. And I can prove, it requires some additional work, that the result is a Cohen-Macaulay shape. Once you know that, you can push it further to the remaining locus. And you indeed get a Harish Chandra module whose restriction is V. And that's how the proof works. So, and that's the end of the talk. Thank you.
Are there any online questions?
And can you name at least some of those 6 exceptional orbits in exceptional?
This looks like some humanity exam in high school. Maybe 6 historical figures. I can tell you what is bad about them.
Yes.
Without naming them. It's kind of, this name calling is not good in modern society.
Yes.
As you may know, even in Russia. So take the closure. The closure may fail to be normal.
Mm-hmm.
It may fail to be normal even in classical types, but then something completely non-normal happens. So for these 6 exceptional rigid orbits,
mm-hmm.
you will have a non-normal dimension 2 slice with bijective normalization.
Uh-huh.
It's kind of it's a fairly pathological behavior.
Mm-hmm. But at least what types are they in?
Essentially all of them. There are, I think, 3 in E8, and maybe 1 in G2, and in G2 I think you take subregular.
Subregular. Uh-huh.
Since
okay.
you, Misha, since you insist. Then 1 in F4, 1 in F7.
Uh-huh. Okay.
And Professor Tengov, as usual.
Yes, I was going to, we should look at any more online questions or comments?
Questions in
historical.
Marxism should be addressed to Pasha.
Okay. So any offline questions? I don't have a question.
Yes, sorry for going back to those canonical and non-canonical quantizations. Do you have some interesting example or whatever kind of a non-canonical quantization where you have this whatever H2 and you take not 0 but something else? What comes up then?
Well, essentially the same thing. So you can think about that this restriction to canonical quantization is A, ideological. So this should give rise to this unipotent representations, and B, for quotational convenience. The other cases can be analyzed essentially for the same price.
Okay, thank you.
More questions? Okay, let's thank Vanya again.
Thank you guys and enjoy the conference.